Welcome back to ECE 501B. We are still in Chapter 7 and may be for another day or two. It's going to take us a little bit more time to get to sort of the final conclusion, which is three letters, SVD, singular value decomposition. That's sort of the high point of Chapter 7. We will get there by introducing concepts dealing with positive matrices or positive operators, and we'll look at some positive matrices and some isometries, whatever that is. But you can think of those as like operators that do rotations. So when you see positive operators, you can think of things expanding and contracting, so distances or lengths, and isometries you can think of as rotation. And if you're thinking about complex numbers, you can represent complex numbers in polar form. They have a magnitude and an angle. And that's the way we will generalize that concept to operators. But before we get there, let me just provide a couple of, or three announcements. One, homework number 8 has been assigned, and it's due the Wednesday night of Thanksgiving break. We can maybe work on that if that's not going to work for you, so let me know. The project is due the 8th of December, and in a month, in 4 weeks, is our final exam. So make sure you're setting your alarm properly for that, because it won't be at 4 o'clock. It will be at 6 o'clock on that Monday during finals week. It's the 16th of December. It will be in this room, but it will be from 6 p.m. to 8 p.m. Yes? You can turn the homework in however you would prefer. You can turn it in earlier than when it's due, which is 11:59 p.m. on that Wednesday. You can turn it in through the Dropbox. You can turn it in however works best for you. That's why you have these different options. Those are the announcements. If you have questions, let me know. But today what I want to do is really just give you some information about block diagonal matrices. I'm going to assume that you can manipulate those or use those, but we'll just sort of establish that that exists, or those particular matrices can be constructed. Then we will talk about positive operators, which really means that if you have a linear map, that linear map needs to be self-adjoint, SA, and when you form its inner product with any vector in your vector space, well, t times that vector inner product with the vector v for any vector v will give you a non-negative result. Then you have a positive operator. That's what we're meaning by an operator being positive. Once we have positive operators, we can actually start talking about square roots. If you have a number, then you can take the square root of that number, and it's easier to do if you have a positive number. So we'll work with positive operators and take the square roots of those, or find square roots of operators, and we'll look at that in terms of matrices. We'll give some definitions, theorems, examples, and proofs dealing with positive operators. We'll need that idea or concept when we get into singular value decomposition. We'll do something similar for these operators called isometries, or isometries. I guess it's isometries. And you may have heard of those in other, or with other descriptions when you're dealing with real vector spaces. Maybe now you have an orthogonal matrix. Maybe you've heard of that. Or if you were dealing with complex vector spaces, you might have heard of unitary operators. But we will refer to the combination of those, meaning either in real or complex vector spaces, as isometries. And we'll look at the definition, examples, and theorems of isometries. But really, if you have an operator S that is an isometry, it's norm preserving. meaning if you simply change the orientation or do a rotation, you're not expanding or contracting that vector. And that's what an isometry is. So this is really the definition of an isometry. This blue line underneath positive operators is really the definition of a positive operator also. I've just done it in an abbreviated form. Let's now look at, to start, really just this idea of block diagonal matrices. Meaning, if we look at this concept, we could say that a block diagonal matrix diagonal matrices are square blockwise matrices of the form, and now I'll just sort of illustrate what the form looks like. It might be an A, a B, a C, all the way down to some K. And those are simply on the block diagonal of this matrix with A, B, all the way to K. Those are square, and I will go ahead and call those submatrices since those are appearing within this larger matrix. But A, B, all the way down to K are square submatrices that live on the diagonal of this larger matrix that's block diagonal. Yes. And A, B, C are not necessarily, down through K, are not necessarily the same size. A could be a 2 by 2. B could be a 4 by 4, but it's square, it's 4 by 4, and so you could have these blocks smaller and bigger, but they're all centered along the diagonal. Does that help? So they don't have to all be the same size. But you can see some generic versions of this. If I gave you a strictly diagonal matrix, its block diagonal with its blocks all 1 by 1. So let's just make that statement. We could say a diagonal matrix and that's just non-zero values on the diagonal, is a special case of a block diagonal where all the blocks are 1 by 1. So a diagonal matrix is a special case of this block diagonal structure. We can also have the other block diagonal, and that's any matrix, where the entire matrix is a single block. So you could have the other extreme that says any matrix is expressible as a block diagonal matrix with 1, the number 1 block. So this is the number 1. Which really begs the question, you need to know the size, and that's what the first question from the class was. Are these A, B, C's through K all the same size, or all the same dimensions, or all these submatrices? Not necessarily, and you need to be told or you need to be able to identify what the sizes of those blocks are. So it's important that you need to be given or be able to identify or to know the size of these subblocks. One thing that you can see, though, is if you perform the product of two block diagonal matrices, and here I'm actually assuming that those two block diagonal matrices are dimensioned compatibly. So the product of two block diagonal matrices, if I had an A that I labeled as A1, A2, let's say down to A sub m, and if I had a B that was a B1, B2, B sub m, those are block diagonal matrices, and I'm assuming then that the A sub j is the same size as B sub j for all the different j's. A1's the same size as B1, A2's the same size as B2, A sub m is the same size as B sub m. If that's the case, then this matrix product, AB, remains block diagonal. AB is block diagonal. And its form is probably what you would anticipate, and you can sort of push that through if you look at that with a specific example, but you now have the product of A1, B1, A2, B2, all the way down to A sub m, B sub m, and that's your only non-zero entries, and those form submatrices that are square along your diagonal, and so your product of these two block diagonals remains block diagonal, where you have A1, B1 as a first block in this product of block diagonals. This is nice to be able to use because the textbook actually uses that in a theorem. So I will simply say that Axler, the textbook, can then use these results of block diagonal matrices to show that a normal operator and now whenever I say normal operator, you know what that means. Is that true? That the operator and its adjoint commute. So the operator is normal. But now if we restrict that to be with a real inner product space, then we can find a representation for that normal operator that is block diagonal with blocks either of size 1 by 1 or 2 by 2. And that's actually Theorem 725 in the textbook, that particular result. So if you have a real inner product space and a normal operator on that real inner product space, that operator can actually, you can find a representation where it's block diagonal, where you might have everything on the diagonal, which if they were 1 by 1 blocks, those would be the eigenvalues. If you have 2 by 2 blocks, those don't have eigenvalues, but those can be represented by 2 by 2 blocks. With that result, we can really sort of represent all of these spectral theorems in 3 different pieces. So let's summarize what our spectral theorems give us. If our space is complex, if our vector space V is complex and our operator T is normal, then the matrix representation of that normal operator T can be diagonal. And actually that's, if it's diagonal, it's a form of a block diagonal, isn't it? That's the first special case. Form of block diagonal. That's sort of the first result when we have a complex inner product space. And our operator T is normal, then the matrix representation is diagonal. So we could think of that as being a diagonal matrix. If V is real, then in order to be diagonalized or have a diagonal representation for the matrix, we need T to be self-adjoint. V is real, T self-adjoint, then the matrix representation of T again can be diagonal. But T being self-adjoint is a little bit stricter than T being normal. But that's what it needs when we're operating on this real vector space. And again, this diagonal matrix is a form of a block diagonal. Now we can relax that a little bit if we're on a real inner product space V and T is normal. Then the matrix representation of T, as we just sort of claimed from that earlier theorem, which we just talked about, theorem 725, then the matrix representation of this normal map on a real inner product space can be, now we are dealing with a real block diagonal matrix with 1 by 1 or and or 2 by 2 subblocks on the diagonal. So those are sort of our ways of finding or obtaining these block diagonal matrices. V being complex, then what do we need? We need our operator to be normal. If we're on a real operating space, we could have 2 possibilities. T being self-adjoint, that gives us a diagonal. But if we don't have that special case, if T is simply normal, then we could have a block diagonal matrix. But we still have these generalized diagonal type matrices if we have normal or self-adjoint operators. That's what leads to these diagonalized structures in our vector spaces. Let's now look at the next kind of operator. So we have linear operators, we have normal operators, we have self-adjoint operators. Now let's look at another one, which is a positive operator. And if you're reading along later on today, this you can find on page 144 of your book. And this says an operator, let's say T, and if it's an operator, it's now mapping between a vector space and itself. So now T is a linear operator on this vector space V, is positive if two conditions. T is self-adjoint which means that T is equal to its adjoint, and if we form the inner product of TV with V, that inner product is non-negative. That's the definition of an operator being positive. It needs to be self-adjoint, and the inner product of TV with V is non-negative. Then we have a positive operator. If we're on a complex vector space, really all we have to have is this second piece, because it's guaranteed that it's self-adjoint. Let me just write that as a note, or try to collapse that down. Note, if V is complex, then T is self-adjoint when TVV gives you a real number. And all of that basically comes to us because of the following. If we had the inner product of TV being greater than or equal to 0, if you remember the terminology in the book, this greater than or equal to 0, when that is potentially complex, if we're saying that that's greater than or equal to 0, that really means that you're dealing with a real non-negative result for that inner product. That's the notation that's being used by the book. So this inner product of TV with V greater than or equal to 0 means it's real and non-negative. And if it's real and non-negative, that means that TVV is real. But if we have TVV being real, then corollary 7.3 says that that operator T is self-adjoint. Meaning if we have TVV being real, then corollary 7.3 implies that T was self-adjoint, and so we really don't need to also say that T is self-adjoint in that definition of T being positive. If we're operating on a complex vector space, then really all we need to show is that TVV is non-negative. Then we have T being positive. All right, so let's just look at, very quickly, some examples of positive operators. And we'll get to more of these in a minute. But here, let's just, before we go any further, let's just look at a couple of examples of a positive operator. If you remember back when we were proving 7-Eleven, I've made such a big deal about 7-Eleven. That was a lemma. And the proof of lemma 7-Eleven, so the proof of lemma 7-Eleven, that spanned a couple of different lectures. When we finished up one lecture and started another, we were dealing with lemma 7-Eleven. The proof of lemma 7-Eleven with T self-adjoint and alpha squared less than 4 beta produces a positive t squared plus alpha t plus beta I. That operator was positive. We demonstrated that that was greater than or equal to 0. This operator, t squared plus alpha t plus beta t. We plugged it into V, or we operated on V, and then we inner product that result with V, and we showed that that inner product was non-negative. So that, we now know that, whatever that means, is a positive operator. We have one example. Another example of a positive operator is every orthogonal projection is positive. Actually, let me say, yeah, that's, so now all of these orthogonal projections, which we may want to do or have done, every orthogonal projection is positive. That's enough examples for now. We'll get into more in a minute. But now that we have these sort of positive ideas or operators, we can think of those as generalizing positive numbers, and I can take the square root of a positive number. So let's now talk about square roots of operators. So we can now define square roots. If we now have S as a linear operator on some vector space V, S is the square root of another linear operator T. I think obviously enough, if we squared S, and that gave us T. So anytime we can find a linear operator that we can operate on it, basically the product, and that gives us this linear operator T, then we can call S a square root of T. Let's look at we'll state a theorem and then we'll show some examples before we even do the proof of the theorem. How's that? So that we can get a little bit better feel for what these ideas are. But first, let's just state a theorem. We're in line 27 of chapter 7, so we're getting deeper into chapter 7. Given a linear operator, T, the following statements are equivalent. Given T, the following are equivalent. So now let's just list several different equivalence statements. A linear operator T is positive. If T is positive, then we can also say that T is self-adjoint. That's not much because that was in our definition of positive. T is self-adjoint, and all of the, can I just say E values for eigenvalues? I'm getting lazy. So all the eigenvalues of T are non-negative. That's sort of nice. If t is positive, then all the eigenvalues of that operator are non-negative. We don't have any negative eigenvalues. That seems to be nice, consistent with t being positive, just if we're thinking about these ideas. If t is positive, then it's b. It's also c. T has a positive square root. Which means we can create a matrix or an operator S that when we have S times S, we get T if T is positive. Another statement that's equivalent is that T has a self-adjoint square root. T has a self-adjoint square root. And the last one is there exists, again, all of these statements are equivalent. There exists an operator, we'll call it S, such that T is equal to the adjoint of S times S as an operator. Let's look at some examples before we get into the proof, just so that we can start to maybe think about what this means instead of just going through the proof and you're going, I don't know what all this means. So let's give some physical examples, or examples, let's say, with matrices. And these examples are going to be square roots and positive matrices. Let's say 1. T1 is equal to 1, 0, 0, 0. And most of these will be 2 by 2, just because you can generalize these to other things. Can you guys find a square root for T1? What's a matrix when multiplied by itself will give you T1? Same matrix, right? Or you could, same structure with a -1. And then that one times itself will give you T1. So you have a couple of square roots at least for this. One would be S1 is 1, 0, 0, 0. That times itself would give you T1. Or let's say we did S1 bar is -1, 0, 0, 0. Do I use bars for complex conjugate? I don't, do I? I'm not meaning that. So let me just say that that's S1 hat. I'll give it a party hat. So it's just something different. S1 of -1, and what's that doing? Well, that's just taking -1 times the top row of itself, and that would just change that sign to give you T1. So S1 times S1 is T1. S1 hat times S1 hat is T2, so that's a square root in matrix terminology. Second one, this one is actually not written this way. It's written with T of X or T of Z1, Z2, Z3 equals something, but I put it in the matrix representation. This is in your textbook on page 145. Here, if you had a T sub 2 equaling, let's say, 0, 0, 1, 0, 0, 0, 0, 0, 0, getting kind of messy on my matrices, but the last two rows are all 0. A square root of that can actually be 0, 1, 0, 0, 0, 1, 0, 0, 0. so that S2 times S2 gives you T2. And you can sort of see this if you simply put that, copy it down, and now you say, oh, the top row needs to be the second row, which is 0, 0, 1. The second row needs to be the third row, which is 0, 0, 0. The third row needs to be 0 times the other three rows, and so you get 0, 0, 0, and you get T2 out of the product of S sub 2 times S sub 2. You can kind of have more going on in the square root than you have in the square with these matrices, if non-zero entries mean more going on. Another one. Suppose we had, these are really, really challenging. Suppose we had T sub 3 as the identity operator. I know it'll take you a couple of years to figure out what that square root's going to be. Or it could be both negatives if you wanted to, but this is the positive square root of T sub 3. What about T sub 4 being a diagonal of 2, 3? Can I include a couple in one? That would work, right? So now you have 4 different square roots of T sub 4 with the different combinations of those numbers. All right, maybe that's not so interesting. Let's look at a fifth one. Suppose that I now give you T5, and that's now 3 minus 4 minus 8 and 11. It's immediately clear that one square root of that is minus 1, 1, 2, minus 3. Actually, I cooked that up. I just said, oh, let me have S5 here. Let me multiply it by itself, and that gave me T5. So now I can go the other direction. Okay, if I want. But I can also find a different square root for that. I could say, maybe I start with the same result, which is 3 minus 4 minus 8 and 11. And I now end up with S6 being 1 minus 1 minus 2, 3. Now S5 I wrote down wrong. Does that look a little bit better? So now S5 better be, my notes are all over the page, so hopefully they get copied down a little bit better once I get to where you're seeing them. But now we should, yeah, that was such a bell ringing result, I wanted to make sure and ring the bell. Okay? I don't know that that got picked up on the microphone, but those in class enjoyed it. But this should be okay for a result. Now you have 2 different square roots. If you actually computed the eigenvalues of the square root of S5, I hope that's what I've actually done. Those, in this case, the square or the eigenvalues of that S5 are at minus 0.2679 and minus 3.732. So that's definitely not a positive matrix, S5. But the eigenvalues of S sub 6, even though it gives you exactly the same product of S6 squared as S5 squared gives you, the eigenvalues of S sub 6 ends up being 0.2679 and positive 3.732. So now you have positive eigenvalues, and S sub 6 is a positive matrix. Although it's not, is it? Because S sub 6 is not self-adjoint. And for S6 to be a positive matrix, it needs to be self-adjoint. So now let's look at some positive matrices. There's sort of some examples of matrices and square roots of matrices. Let's now look at positive matrices or potential matrices and see if they are or are not positive. So which Q's are positive? 1. Suppose that I now had Q1 equal to 1, 0, 0, 2. Do you want to guess positive or not? What's it need to be positive? By definition, it needs to be self-adjoint, which means Q and its adjoint need to be the same, and it needs to have positive eigenvalue. Well, it needs to be Q1, the inner product of Q1 with any vector V times V, or with V, inner product, needs to be non-negative. In this case, Q1 is self-adjoint, isn't it? So Q1 is self-adjoint. Now let's just look at the inner product. Q1V, and this is sort of one way of thinking about what's going to happen. Now you have this inner product of a matrix with V, and let me just make V have a couple of coordinates. If I form the first matrix vector product, I now have a vector V1 with 2 V2. And now I have V1 squared plus 2 V sub 2 squared, and I hope that it's clear that that's non-negative for any V or for all V. And let me just go ahead and make those real for now because we're dealing with easy examples where V was this two-dimensional vector. Okay, so this Q1 being symmetric, it's equal to its transpose, so it's self-adjoint, and now we can compute the inner product, and that gives us this quantity of coordinates squared weighted, a weighted squaring of coordinates by that structure of Q1. And it's pretty clear how they are weighted based on the structure of Q1. Suppose now we looked at another Q, so that Q was positive, wasn't it? Maybe I should say that. So Q1 is positive. Second example, suppose that Q sub 2 is now 2 minus 1 minus 1, 4. Is Q sub 2 self-adjoint? Yes. So Q sub 2 is self-adjoint. We're living in this real vector space again. Now if we look at Q sub 2 V, V, In our first vector, we have 2v1 minus v2 in that first coordinate. And in the second coordinate, we have minus v1 plus 4v2. And we want to form the inner product of that vector with v1, v2. Or we now have 2v1 minus v2 times v1 plus minus v1 plus 4v2 times v2. Or this is now 2v1 squared minus v2v1 minus v1 v2 plus 4 v sub 2 squared. And I can factor out a 2 from all of that and maybe minimize some of this. I now have v1 squared minus, and those scalars commute, so I now have minus v1 v2 plus 2 v sub 2 squared. But I can now complete the square, can't I? I can now say, well, let me just keep that 2 out front. I now have v1 minus 1/2 v2 squared. And that will give me v1 squared minus v1 v2 plus 1/4 v2 squared. And if I subtract that 1/4 v2 squared, I still have that 2 v sub 2 squared in the original description. Or I now have, this is 2 v1 minus 1/2 v sub 2 squared plus 7/4 v sub 2 squared, which is greater than or equal to 0. And so Q2 is a positive matrix. Is that okay? So for any v1 and v2, that's going to give us a non-negative result. What about one more? Let's look at one more. Suppose Q sub 3 is now 2 minus 4 minus 4, 4. Is Q sub 3 self-adjoint? It is. So now Q sub 3 is self-adjoint, and let's now look at Q sub 3 v as an inner product. We now have 2v1 minus 4v2 and minus 4v1 plus 4v2 that we will now take the inner product with v1, v2. Or that's now 2v1 minus 4v2 times v1 plus a minus 4v1 plus 4v sub 2 times v sub 2. We can factor out the 2 again, and we have v1 squared minus 4 v1 v2 plus 2 v sub 2 squared. If we complete the square in the first two terms, we have v1 minus 2 v2 squared. And now I have a plus 4 v sub 2 squared that I introduced. I now need to subtract that. And if I bring down the other v sub 2 that I started with, which was 2 v sub 2 squared, I now have a result that says 2 times v1 minus 2 v sub 2 squared minus 2v sub 2 squared. What can I say about that? That one's indeterminate, isn't it? I can't make it be a strict sign of negative or positive. So this is actually indeterminate. Because I could, for the appropriate choice of v, suppose I had Q3VV, I could make that less than 0 for v equal to 0, 1. Can I, or is it actually going to be, you know what, I was just assuming, I wasn't even assuming that first piece was there, but now I have 4v squared minus 4v squared, so it's 0, isn't it? So this one maybe is not the best choice, but maybe I could do a 1, 1, and that would be better. If I do that, now I have 1 minus 2, so I have 1 squared minus 2, so that's going to work. Whereas I could choose Q sub 3v to be positive when v is 1, 0. And if I actually looked at the eigenvalues of Q sub 3, I would see that I had one was negative, minus 1.123, and the other one is positive 7.123. So there's a Q sub 3 that's not positive. And we could have, if we wanted, depending on what we had the ability to do, we could say, oh, Q3 is self-adjoint, but let me find the eigenvalues. Oh, one's negative. It's not going to be positive. So Q sub 3, that gives you some ideas or some numerical matrices that are positive. We can think of square roots, what those look like, etc. Now we can maybe go back to our theorem. Wow, where was it? Where we had all of these equivalent statements. And let's prove this. If we have statements that are equivalent, if we can show A implies B, B implies C, C implies D, D implies E, and if E implies A, we're done, right? So that's what we'll do. We'll just show that these 5 statements are equivalent by showing sort of their individual equivalence. So first, let's look at T being positive and T self-adjoint and all eigenvalues are non-negative. Because we've already sort of used that, but let's go ahead and now look at the proof of whatever that was. Had a couple of 7s in there, 727. Ooh, some of you may have even made it to Tucson on 727 and you didn't even know it was a theorem, did you? So now we have a theorem 727. We have a quick store, 7-Eleven, we have an airplane. Who knows what we're going to have in this particular textbook? Hidden. So this is now a theorem 727, and again we're going to look at A implies B implies C implies D implies E implies A. That's sort of our approach. So let's look at the first case where A implies B. And if we recall the definition, that already gives us part of B, doesn't it? T being positive says that T is self-adjoint and TVV is non-negative for all v in our vector space capital V. So we've already proven the first part of B, that T is self-adjoint when T is positive. That's by definition of T being positive. So now let's use this second result. We're given that because of it being a positive operator. But now let's let V be a special vector. It's true for all vectors, but let's let V be an eigenvector. Since it holds true for all vectors, let's just look at an eigenvector and see if we can get a result, because we're trying to show that all the eigenvectors are non-negative. Or I'm sorry, all the eigenvalues are non-negative. So if TV V is in our inner product, we can replace TV with lambda sub I V. Or maybe I don't want to specialize lambda. Let's just say it's any generic eigenvector V. It's all n of those, so let's just say it's lambda V. That's greater than or equal to 0. But we know the properties of the inner product. That first slot, the scaling factor, can be pulled out directly, and now we have the lambda scaling the inner product of V with itself. And we know V inner product with itself is non-negative. Therefore, lambda is non-negative. So that now shows that A implies B, just by saying that B was positive. Now let's look at B implies C. And I'm going to cheat. I'm going to go back and say, okay, T is self-adjoint, and we know all the eigenvalues are non-negative. And we want to show that T has a positive square root. So this is a nice one, because this is actually going to be a proof by construction, and we'll be able to use this to find square roots of matrices. So B implies C. T is self-adjoint. That's part of B, wasn't it? B was T is self-adjoint. And if T is self-adjoint, we now can find an orthonormal basis for that vector space where those from the spectral theorem. So we now have, E1, all of the eigenvectors of T form an orthonormal basis for our vector space V from the spectral theorem. So E1 through En form an orthonormal basis from the spectral theorem. Now, we not only know that T is self-adjoint, we also know that all the lambdas are non-negative. That's B. Those are the in statement B. So now what we are going to do is let's go ahead and build the square root. So now let's let, or define, however you want to phrase it, define S, the matrix S. If we multiplied it by a orthonormal basis vector E sub j, let's let that be the square root of lambda sub j e to the j. And this is true for all j. J equal 1, 2, up to n. Now, do I want to sort of say what we have? You could sort of see this, so this maybe isn't that clear, but suppose that I now just sort of did an aside and show you what this is really meaning. suppose I had the matrix S, which I don't yet know what it is. But I know that when I multiply it by E1, I want that to be a scaled E1. And I want to scale E1 by this square root of lambda sub 1. So I want to take E1 and I want to scale it by the square root of lambda sub 1. So the square root of lambda 1 is going to go in this 1, 1 entry, and it's going to scale everything in E1, and there's not going to be anything left in that column below the square root of lambda 1. If I look at E sub 2, that scaling or multiplied by S, so I'm building up a matrix, and these E1s are columns. E1, E2, these are columns. I now have the second column, E sub 2, is going to get scaled by the square root of lambda sub 2. And I'm running out of room, but I have an infinitely wide piece of paper. But if I do this, if I keep going, I think you see the pattern that I'm trying to establish. In this first definition statement or line, Sej is square root of lambda j Ej, I just wrote down in matrix form. I just wrote all n of those down in one equation. But now, what do I know about the e's? Those are an orthonormal basis. They fill up the entire space, so they have an inverse. Meaning, I can now post-multiply on the right, on both sides of this equation, by the inverse of this orthonormal set of basis vectors. And that will give me my S. Why? Because these E sub j's were the eigenvectors associated with this given operator T. So T, if I have that as an operator, I can find its eigenvectors, and I can create those to be orthonormal. So I now have these E's. I have E1 through En, and I also know, or can compute, the eigenvalues of T, which allows me to build up this other than the S matrix. But now I have an expression for S. If I call this E, and this is E, then S is equal to E, and what do I want to call this other matrix? Well, I'll just do it lambda 1, lambda sub 2 square root, lambda sub n, 0, 0. And in fact, if that's the inverse of this orthonormal, that's the transpose. But we'll just make it as clean as possible and say I can invert that, so this is now E inverse. There is my constructed S matrix. And we want that to be a positive square root. Well, all of these numbers on the diagonal are positive, and all of these E's are basically of length 1, aren't they? So you could, in a basis, in the appropriate basis, this matrix S could just be this diagonal matrix that's positive. So S is going to be a positive matrix. That was our sort of aside in this very first step of showing that B implies C. B was T is self-adjoint and all of its eigenvalues are non-negative. We now said, well, then define an S such that Sej is the square root of lambda j Ej. All right. Then I just sort of showed you this construction technique, but that's not a part of the proof necessarily, but now you know that that makes sense. Step 1 does. Now, if we do S squared E sub j, that's now SEJ was lambda, square root of lambda sub j EJ. But now if I multiply that by S again, the square root of lambda j slides through S and I have SEJ. But SEJ is the square root of lambda j EJ. So this now gives me lambda sub j EJ. I kind of like that, lambda j EJ. I don't know why. It sounds like a name or something. So now we have this character EJ. It's E sub j. But lambda sub j E sub j is the j eigenvalue eigenvector of t by definition. So this is now t E sub j. And this is true for all j. But if that's the case, an E sub j is an orthonormal basis vector, so you could stack all of those up again in a matrix, divide out that matrix capital E, and you have t is s squared. So s, by definition now, is the square root of t. And it's a positive square root because of how it was constructed out of these positive square roots of the eigenvalues of t. So, what have we concluded? Now we know that s is a square root, and it's actually a positive square root that you can see from the construction that we used, but we'll just go ahead and say s is positive. That was hopefully clear from the construction. But if s is positive, in the definition of a matrix being positive, we know it's self-adjoint. And we now know that it can be, if it's it can be diagonal in the E sub j basis, or in this basis of eigenvectors. Consequently, if we looked at SVV as the inner product, that's actually going to be the sum over j of these a sub j squared, square root of lambda sub j, and that's greater than or equal to 0. And what we did in this last step is we basically said, suppose that V is just some vector in this vector space, which means that we can write it as a linear combination of these basis vectors, E1 through En. That's V. But now if we operate on V with S, that's now A1S E1. A1 are coefficients, aren't they? Plus 8, so they slide through. But by construction, what were the SEs? Those were these square root of lambdas, weren't they? E's. So this SV becomes A1 square root of lambda 1 E1 plus A sub 2 square root of lambda sub 2 E sub 2 by construction of S. And now if we put that in this inner product with the V, which again was the A1, E1, A2, E2, we now simply are taking an inner product with orthonormal basis vectors. Those are the Kronecker delta. They just become 1 when the subscripts are equal, and they 0 when they're not. And we're left then with A1 times A1, and if 1's complex, we've got the conjugate, so we have A1 times its conjugate, which is the magnitude of A1 squared, times the square root of lambda 1, and I think that's what we were saying up here in this sum. We now have these coefficients, magnitude squared, for each j scaled by this square root of lambda j, and the square root of lambda j was positive, as is this magnitude of the coefficient. So we're guaranteeing that that construction produces a positive square root, because SV, inner product with V, is non-negative. Is that clear? So that's now proving B implies C. If we now look at the other one, C implies D, this one's easy because I think it says, well, what was D? Got too many. T is supposed to be self-adjoint or has a self-adjoint square root. But because C says that S is positive, then it's self-adjoint by definition. So this was basically given. C was that S was positive, so positive implies, by definition, that it's self-adjoint. So C implies D. D implies E. Now S is self-adjoint. With S squared giving us T, because S was the square root. Well, T then, and what we're trying to show now is that there exists an operator T that's equal to its adjoint times, or an adjoint times itself. So S adjoint S. So T now is equal to S squared, but S squared is S times S, but S is self-adjoint, so S is equal to its adjoint, so I can replace the first S with its adjoint and then just follow it with the S, and that's what we needed to do. So here in this step, I used the fact that S was self-adjoint. One more. We need to catch our tail, which means we need E to imply A. And then we will have proved 727. So now E was that T can be written as S adjoint S. So T is now equal to S adjoint S. But we can now rewrite that, or we can use that to write T at the adjoint of T, which says that that's just S adjoint S adjoint. And if we really break this down, that's now the what? Sort of the second one adjointed, and then the first one following, which is the adjoint of the adjoint. Is that okay? That's really what we're doing. And if we sort of skip that step, we could have immediately written down that S adjoint is just S adjoint, and the adjoint of S adjoint is S. So the adjoint of T is now S adjoint S. Wait a minute. That's what T was. Good. So now T is self-adjoint, right? And what do we need to do now? Now we need to show that it's non-negative when we form the appropriate inner product. So now for the second part of A, we can look at, or we can watch TV, TV, comma V, inner product, but that by definition was S dagger SVV. But we know how to use the inner product, we can now put that S dagger in the second slot with its adjoint. And the adjoint of S dagger is S. So now we have S is S dagger dagger V. But that's just SV is SV, which is non-negative by the positivity of the inner product. So we're done. Let me just write that down. So that's by the positivity of the inner product. Therefore, T is positive, which says that E implies A, and we're done with 2 minutes overtime. So hopefully that won't happen tonight, and you have enough time to get to the game at 9, and we will pick up at that point. You're staring at me like you don't know what I'm talking about, but at least you were not staring with a blank glaze in the rest of the lecture, which is the best part. So I'll see you on Wednesday.